Next one is looking at the fuel spray behavior. This feature is showing the schematic of the preferred geometric targeting arrangement of fuel injector and intake valve head for the PFI method. Also shown in this feature is the dimension in millimeters. On the top one here is the side view, and this one is the bottom or top view. Looking at this schematic, the spray is injected toward the back side of the intake valve, this one. So we will expect having a decent film formation at the back side of the intake valve. So this film will need a time to be evaporated and then entering the cylinder. So usually in the PFI type injection, the film stay in the intake manifold around 10%, and it will go to the cylinder in the next cycle. This feature showing the detailed schematic of the liquid fuel behavior. So we have a PFI again here injected upstream of the intake valve. So this is the intake valve and this is the injector. Point number one here is the spray that just exit the injector, and then some of this spray will be carried out by air as a droplet, okay, and it will enter the cylinder, and then the rest will stay in the intake port as a surface film attached to the intake valve, so mostly at the back side of the intake valve. And then point number two, so this one is the droplet that is carried out by airflow. Some of this droplet will evaporate, okay, there will be a heat transfer from the airflow to the droplet, therefore it's also give a benefit in terms of the charged air cooling. And then the rest will be as the wall film attached to the cylinder liner. So it's number 4. 4 is here. Here's number 4. Okay. And then back again to number 3, which is the surface film attached to the back side of the intake valve. With the time, some of this liquid film will evaporate, and if the intake valve is still open, it will go to the cylinder at the same cycle. Otherwise, it will stay in the intake port and then will be admitted to the cylinder in the next engine cycle. The other liquid film or surface film will be atomized by the airflow, because there is a direct contact between the airflow and the liquid film, so that there will be an atomization as well. Okay, and then some of this atomized fuel will be carried out by the airflow entering the cylinder. So you can see you have number 2 here, but this one is coming from the atomization of the liquid film attached to the intake valve surface, and then the rest will flow to the in cylinder, and it will interact with the wall and then forming another film. So it's number 4. So this portion is the same as this one, but it's coming from different source. And then the droplet that is carried out by airflow number 2 will follow the same path. So some of this droplet will be evaporated to be vaporized fuel, and then the rest will be attached to the cylinder wall as the film. So depending on the thickness of the wall film and then the local temperature in contact with the wall film, either this wall film will be atomized to vaporized fuel and then it is burned during the combustion process, or it will stay in the wall, and this will be one of the source for the unburned hydrocarbon, because some of this liquid film will be scrapped by the piston during the exhaust stroke, and once again this is one of the source for the unburned hydrocarbon emission. So we'll look at this in more detail in chapter 12, I think, when we talk about the engine emission. Back into the direct fuel injection, beside the primary benefit of this direct fuel injection method, so we also have a secondary benefits. So the first one here is that the fuel evaporation within the air charge in the cylinder cools the charge, so that it's allowing higher compression ratio to be used since the cooling delays the onset of knock. So knock is strongly dependent on the mixture temperature. So if we can have a lower temperature, it will lower the propensity to knock. So one of the way to reduce the knock propensity is by having a cool mixture at the start of the compression or during the intake stroke. And then it also results in the engine inducting more air, thereby increasing wide open throttle torque. So this idea is similar to the one using a turbocharger. So in this case, we have a lower temperature of the mixture, which result in lower mixture density and thus having more trapped mass. And then we can also have a tighter control of mixture preparation, so and especially stratified overall leans operation. It's improved the engine specific fuel consumption, engine thermal efficiency. So for the stratified lean operation, we can have a stoichiometric mixture around the spark plug only, and then having a lean mixture far from this spark plug zone, and the overall mixture composition will be a lean mixture. And we know from the thermal efficiency dependent on the compression ratio and specific heat ratio that lean mixture increases the specific heat ratio, and the specific heat ratio increases the engine thermal efficiency. So thus direct fuel injection offer increase of the output because the increase of the air density, higher fuel conversion efficiency, especially for the stratified leans operation, because the overall mixture condition is lean mixture, and thus higher specific heat ratio, and finally better thermal efficiency. But this one is the disadvantage of this direct injection type. So the fuel system cost is the most expensive compared to the other fuel delivery system. As has been mentioned in the previous slide, with the direct injection, we can control this system to produce homogeneous mixture at the end of the compression stroke, or stratified mixture at the end of the compression stroke. So at the end of the compression stroke, here is the event where we have the spark ignition process. To have a homogeneous mixture, the fuel need to be injected during the intake stroke, while for having stratified mixture, the fuel need to be injected during the early phase of the compression stroke. This table is showing a major mixture preparation features of homogeneous and stratified mixture for direct injection spark ignition engine. The first column on the left side is showing the feature, and then second column is for homogeneous mixture, and the third column is for stratified mixture. Let's take a look one by one of this feature. The first feature here is about the load and speed range. So homogeneous mixture is usually operated for full load and speed range, and then for stratified mixture it is operated for part load and then low to mid speed. Second feature here is a naturally aspirated or turbocharger. So we can apply both NA and turbocharger here for homogeneous mixture, as well as stratified mixture. Here we can operate both NA and this turbocharger as well. And then the third feature is about the stoichiometry. For homogeneous mixture, usually we have a stoichiometric mixture, so stoichiometric air-fuel ratio. For stratified mixture, so we have a Lynch mixture in overall. Locally, so it's mean this is at the spark plug or around the spark plug, we have a close to stoichiometric mixture. So the reason for having stoichiometric mixture around the spark plug is to have a successful ignition process. The next feature is for the mixture preparation approach. For homogeneous mixture, usually we have an early injection. So to have a homogeneous mixture, and then we need to provide decent time for the fuel to mix with the air and maybe EGR. So in this case, usually we inject the fuel during the mid-intake stroke, and then we can have a wide spray dispersion. So it's mean it will enhance the spray evaporation. For the stratified mixture, we can have a late injection. So in this case, we inject the fuel during mid to late compression stroke. And then we can have a conveyed mixture cloud around the spark plug. Once again, we can have a stratified mixture. So around the spark plug, it is stoichiometric mixture, and then surrounded by a cloud, which is a Lynch mixture. So once we have a decent flame size, then it doesn't matter if we have a Lynch mixture, because this flame size should be strong enough, should be large enough to have a successful combustion throughout the chamber which have a Lynch mixture. And then the next one is for the fuel injector location. For homogeneous mixture, the fuel injector location is usually below the intake port. You can have a look in the previous slide. I think there is one schematic of the GDI with the injector located under or below the intake port. And then for the stratified mixture, either we can have the injector location below the intake port, or it is close to the spark plug. So for close to the spark plug, usually we have a narrow spacing. So narrow here it means that we have a small distance between the spark plug and the injector. For the injector design, usually we have a multi-hole nozzle with a wide spray angle for homogeneous mixture. Once again, we need to have a good injection system for homogeneous mixture. So one of the way to have a good injection system for having homogeneous mixture is by having a multi-hole nozzle injector. So the hole size is smaller and the hole number is more. And then for the stratified mixture, so various design to fit with stratified combustion approach is available here. So because it is stratified, you can have a smaller number of nozzle, you can have slightly larger nozzle diameter. And then regarding the fuel injection pressure, for the homogeneous mixture, we typically have injection pressure of between 5 to 15 megapascal or 50 to 150 bar. And then for the stratified mixture, similar, so slightly higher upper limit of this pressure, so 200 bar. Latest research by Southwest Research Institute so that having a higher injection pressure still give a benefit for this GDI. So last year we did a research on looking at 500 bar injection pressure, and we did see the improvement of the engine PSFC. So having high injection pressure means that we need to put more energy, and this is parasitic energy because it is used to increase this injection pressure, and this is coming from the engine power. So as long as the engine power increase can offset or higher than the increase of this injection pressure energy, then it is good. So it means we can gain some engine efficiency due to the higher fuel injection pressure. The next one is looking at the airflow. So for homogeneous mixture, usually we have a tumble type airflow. So we will look at tumble, swirl, and so on in the next chapter. So once again, for the tumble mixture, usually we use a tumble type airflow. In this case, we have a rotation flow about the X and Y, or X and Y here is perpendicular to the cylinder axis. So cylinder axis usually in the Z axis. For the stratified mixture, we can have a tumble flow or swirl flow to match with spray, and it is combined with the ball in piston geometry. So ball in pistons, it means that we have a kind of ball at the piston top surface. And next one is the piston geometry. So for the homogeneous mixture, usually it is close to conventional piston crown design. So usually it's simple. The design is simple. For the stratified mixture, usually we need to have a ball in piston. So this ball in piston is used to direct and convey developing fuel spray. And the last one here is looking at the emission control approach. So for homogeneous mixture, we have a three-way catalyst to remove unburned hydrocarbon, CO, and NOx. And then for having a better emission, we can retard the spark timing. So the reason having spark timing retarding is to lower the combustion temperature and thus a better NOx. So in chapter 11 or 12, when we talk about the emission, we will see how does the temperature impact the NOx emission. For the stratified mixture, we also need to retard the spark, and then we can have a Lynch mixture combined with the EGR. So Lynch mixture produce a lower combustion temperature, which is good for the NOx emission. And then we can also have a lean NOx storage catalyst. This picture is showing the schematic of two major categories of mixture preparation for ignition and combustion used in direct injection stratified charged spark ignition engine. On the left schematic, A here is widely spaced injector and spark plug is shown. So you can see that the injector is located below the intake system. And then on type B, we have a closely spaced injector and spark plug. So you can see there that the injector tip is very close to the spark plug. For the type A, the fuel spray here is guided by the wall. So you can see here we have a special type of the piston crown here that will guide the spray and then deflect it, and then it will create a stratified mixture. The spray is also guided by the airflow. So the arrow, black arrow here is showing a kind of the airflow pattern. So once again, the purpose of having this fuel spray in the stratified charged spark ignition engine is to have a close to stoichiometric mixture around the spark plug. So I can put here as a red here. So we need to have a close to stoichiometric mixture around the spark plug, and then the other zone here we can have a Lynch mixture. So all other zone here we can have a Lynch mixture. So with this strategy, we can have overall Lynch mixture, which will improve the engine thermal efficiency because of higher specific heat ratio and also lower combustion temperature, and thus a lower wall heat transfer. But once again, the key point here is to have a stoichiometric mixture around the spark plug so that we will have a successful ignition process. And then for the type B here, the fuel mixture composition will be guided by the characteristic of the spray. So you can see on the schematic there that we have a kind of unique injector that can produce a wide spray angle. So here I put a purple. So it can produce a wide spray angle in such a way that at the end of the compression stroke or during the ignition process, we have a close to stoichiometric mixture in this zone, so around the spark plug, and then overall Lynch mixture on the other zone. So this schematic is showing two different strategy for having a stratified mixture condition. This picture is showing engines that use the stratified mixture for their operation. On the left side, we have a Mitsubishi. So Mitsubishi engine use a reverse tumble, which is combined by a unique feature of the piston here to have a stratified mixture, and then they also have a kind of the swirling spray. So they have a reverse tumble for the airflow and then swirling spray for the fuel injection, plus a unique feature of the piston to generate a stratified mixture. On the next column we have Nissan. So Nissan use a swirl flow. So this is the swirl airflow. Swirl flow is rotation flow about the engine axis, so you can see from this schematic. And then they combine this swirl flow with asymmetric swirling spray, and this is the piston crown surface. And then the next one we have a Toyota. So to have a stratified mixture condition, Toyota use a swirl and then a fan spray. So this is the schematic of the fan spray. So it has a wide angle spray in one side, and on the other side it has a very narrow spray. That's why it's called fan shaped spray. And they also have a unique feature of the piston that guide the spray. So you can see here on this schematic. So let me put a yellow color. So this is a unique feature of the piston that guide the spray in such a way that it will produce a stratified mixture inside the cylinder chamber. Last one, we have a Volkswagen. So they have a tumble flow, okay, for the airflow, combined with a hollow swirling spray. So it's called hollow. So I can make a simple schematic of the hollow spray. So let's start with the solid spray. So the solid spray, so usually we have this spray. So it's mean here all is the fuel spray. And then for the hollow spray, so we can have like this one. Okay, so it's mean in the middle here we don't have a spray, so it's a void zone there. So once again, this is showing 4 different engines that utilize a stratified mixture operating condition to improve the engine efficiency. An important feature of a DI mixture preparation is the charge cooling that occurs due to the in-cylinder evaporation of the fuel droplets as the fuel spray moves through the chamber. In this case, we assume that the fuel spray evaporation is 100% from the air mixture. And then by drawing the thermal energy required to vaporize the liquid fuel from the in-cylinder gases, these gases are cooled significantly. So this formula is showing the estimated temperature decreases when we have this charged air cooling. So delta T equal to MF. MF is the fuel mass time HFG, so this is the evaporation heat of the fuel, and then the time 1 minus XR. I think this formula is not correct, so this one is from equation 7.14, so it's from the second version of the book. I think this is not correct. So assuming that the initial mixture temperature is the same, so the fuel temperature, airflow temperature, residual temperature, all are the same, then I think the delta T should be, so we don't have this one, and then this one is plus, so I remove this one, plus M residual, okay, and then close the bracket times Cp. So this should be the correct formula to estimate the temperature decrease due to this charged air cooling from the evaporation heat. By using the formula shown in the previous slide, then we can estimate the temperature reduction due to this fuel evaporation. Let me write it down again, the formula. So we have delta T equals to M fuel time the heat of evaporation for the fuel, so it is Fg, and then divided by Ma plus Mf plus Mr, so Mr here is the residual mass, time Cp. Okay, so this table is showing evaporative cooling effect of fuel drop in stoichiometric mixture of liquid spark ignition engine fuel. On the first column, you can see we have a different fuel type. So we have gasoline, ethanol, and then ethanol, water, and then methanol. And then second column is showing the stoichiometric air-fuel ratio. Okay. And then next column is showing the heat of evaporation. And then last column here is showing the temperature decrease, okay, due to this fuel evaporation. So what you can see here is that ethanol has much higher temperature decrease compared to gasoline. And the reason for this is because ethanol has a much higher heat of evaporation compared to gasoline. So this is one of the benefit by having ethanol blended to gasoline, so it will result in lower temperature at the beginning of the compression stroke, which will result in less knock propensity inside the engine. This feature is showing the result of the mixture temperature reduction at top dead center or at the end of the compression stroke. So it is the feature on the left side, and also showing the decrease in the in-cylinder gas mixture specific volume. So this is the inverse of the density at the end of the intake process. So the feature is on the right side as a function of the initial air and fuel temperature for 100 and 0% fuel evaporation of the walls. Also shown the data of the air to fuel ratio and then pressure, and this one is for isooctane fuel. So as the isooctane fuel is usually used as a surrogate for a gasoline fuel. Let's take a look on the feature for the temperature difference, so the left side feature. So in the horizontal axis we have the air temperature, and then the fuel temperature is shown by the dashed line. So we have a different fuel temperature here, starting from 0 degree, 90 degree, and 100 degree C. And then the vertical axis here is showing the temperature difference. Okay, and this data is shown for a wide range condition, so where we have a 0% fuel evaporation from air. So it's mean that 100% of the energy used to vaporize fuel is coming from the wall. and we use this one as the baseline. So this point, let me put with the blue. So this one, for this point, so we have 100% energy from the wall that is used to vaporize the fuel. Therefore, we don't have the temperature difference here, 0. Okay, and then once we have more fuel evaporated from the airflow or from the mixture, then we will gain some of the cooling here. So in this case, we have 100% of the fuel evaporation coming from the mixture energy. So in this case, we have this condition. Okay, so for example, if we have air temperature of 100 degrees C, okay, in this one, and then the fuel temperature is 50 degrees C, so it's mean this one, this line. So then the temperature different, okay, temperature different because of this charged air cooling, then we have the temperature decrease of about, let's say here is minus 55. Okay, once again, if we have a air temperature of 100 degrees C and then fuel temperature of 50 degrees C, and 100% of the energy used to vaporize the fuel is coming from the mixture, then at the end of the process, we will have the temperature reduction of around, let's say, 55 here. Okay. And then similarly on the right side, it's showing the cylinder gas mixture specific volume at the end of the intake process. So this one is in case we have 100% fuel evaporation, and this coming from the wall, and this one is 100% fuel evaporation, energy is coming from the mixture. Then you can see in here that there will be a reduction of specific volume of 5%. It's mean we will have an increase of the mixture density of 5% when we have the air temperature of 100 degrees C and then fuel temperature of 50 degrees C. And once again, 100% of the evaporation energy is coming from the mixture energy. This picture is showing a layout schematic of direct injection engine management system. It looks very crowded. So the fresh mixture entering the engine coming from this side, okay, and then we have a sensor there for the air mass meter, and then it will flow through this path. Oh, we have a turbocharger here, so let me put a yellow. This is a turbocharger. So the airflow entering the compressor side, and then it will exit the compressor and then flow through this path. So exiting the compressor, the mixture pressure and temperature increases, and then it will follow this path. And then, okay, we have a charged air cooler. So see here, this is a charged air cooler. So the purpose of having charged air cooler is to lower the temperature of the mixture so that we can have even a better volumetric efficiency. And then next one, we have several pressure and temperature sensor. And then this one is a throttle devices, this one, okay. And all of these devices is controlled by the ECU. So this is the ECU. And then go next, we have the intake manifold here, and then the fresh mixture entering the engine through this path. And this one is the injector, so the very dark color part here. So this is the injector, okay. And then we have the intake valve, exhaust valve, and this one is the spark plug. This one is the piston. We have several sensor attached to the cylinder. So we have knock sensor, we have a temperature sensor, and so on. and then it exits the engine through this side. So let me put red color. So this is where we have the burn gas exiting the engine, and then it is connected to the turbine side of the turbocharger. So this is the turbine, and then we have a wastegate. So you see here, this is a bypass path, okay, and then it will flow to the after treatment system. So we have oxygen sensor. We will see this oxygen sensor in the next slide. And then we have a pre-catalyst, and then another oxygen sensor, and this one is the main catalyst. It very probably is three-way catalyst. So you can see in here that the injector is below the intake system. So let me put purple color here. So you can see in here that the injector is located below the intake system. This is a typical stratified GDI engine operating map with a different operating regime. Let's look at one by one. On the horizontal axis, we have the engine speed, and then on the vertical axis, we have the engine load. For a part load operating condition and at low engine speed, usually we have a stratified mixture operating condition. So in this case, we can have a lead injection. So during compression stroke, and then lambda is above 1. So it's mean we have overall lens mixture, and then it is combined with some EGR. So for this part load and low engine speed, usually you want to have a low NOx, and then you want to have a good engine operation stability, and then also a good fuel consumption. For the part load and higher engine speed, usually we operate the engine under homogeneous mixture condition. So in this case, we need to have earlier fuel injection during the intake stroke, and then lambda equal to 1 or V equal to 1. So it's mean we have a stoichiometric mixture plus a very high EGR. So the purpose of this is to have a good fuel consumption, and then you want to have a low hydrocarbon so that we operate it under homogeneous and stoichiometric mixture condition, and you want to have a good engine stability. For the full load operating condition, so it is on this regime. So this is around the full load condition. We operate the engine under homogeneous mixture. So in this case, we need to have a early injection during the intake stroke, and then we also need to have a octane requirement. So it's mean we need to have a fuel with a decent octane number to avoid knocking. And then we also need to have a good air utilization and thus a better volumetric efficiency. So this is an example of the typical stratified GDI engine operating map. The feature on the left side here is showing a high pressure DI fuel injector layout diagram. You can see there it has a decent component number. So it has a spring number 2 here, and then number 3 here it has a coil, and then a nozzle needle number 4, and then guide washer, and then throttle plate, seat washer, and so on. And then the feature on the right side, B here, is showing signal profiles for activating this injector. So on the top feature, we have a triggering signal that is calculated by engine ECU. And then the next one is showing the output of the injector current. So this current is transferred to the injector, which is used to govern the needle leaf profile as shown in C. So C here is showing the needle leaf profile. And then the amount of the injected fuel is shown in the last profile here, D. So you can see there that the amount of the injected fuel increases with the time and then through the end of the injection event, this one. This picture is showing three types of high pressure injector nozzle and the spray pattern they generate. On the left side we have a swirl nozzle, so you can see here the spray inside the nozzle is generating a rotation flow about the nozzle axis, and the feature on the bottom side is showing the spray pattern exiting the injector. And then on B here we have what's called outward opening nozzle. So we have a wide spray angle generated by this nozzle type. And then C, we have an injector with a multi-hole nozzle. So looking at this feature, it has at least four hole in this injector. So combined with the engine feature, this injector will generate a unique spray pattern. Either it is used for a stratified operation or homogeneous operation condition. Next topic is exhaust gas oxygen sensor. For an engine that use a three-way catalyst to remove unburned hydrocarbon and then CO and oxides of nitrogen, this component is very vital. So a three-way catalyst is a very powerful emission equipment to remove all these three emissions altogether. However, there is a stringent requirement for the effectiveness of this catalyst, that the engine must be operated close to the stoichiometric operating condition. So to control or to check that the engine is always operated under this stoichiometric condition, we use an oxygen sensor, so which measure the oxygen at the exhaust system, and then to make sure that the mixture condition inside the engine is always close to the stoichiometric condition. And this signal is the input to a feedback system which control the fuel and air feeds to the engine cylinders. This picture is showing a cross-section drawing of exhaust oxygen sensor. The exhaust gas is coming from this direction, and this is the oxygen sensor. You can see it has a different component in it. So this sensor measures the oxygen inside the exhaust gas, which can be used to estimate what is lambda and phi. And depending on the resulted lambda and phi, the ECU can adjust the amount of the air flow as well as the fuel flow to have these two number equal to 1. So it's close to the stoichiometric mixture. Next one is the fuel supply systems. Fuel supply and delivery with intake manifold injection have evolved through several stages, and there are two critical requirements for a fuel supply system. Number one is that the system must ensure that adequate fuel is available to the injector for any conceivable change in demands. Second one is that it must enable high injection precision, both cylinder to cylinder and cycle to cycle. This picture is showing different fuel supply and delivery system with manifold and fuel injection. On the A, we have a system with fuel return to the tank. So fuel return to the tank is shown in this side. So this is the fuel return to the tank, this one. Okay, so the fuel is injected, pump it, and then going up through this line, and then some of the fuel will return to the fuel tank through this path. And then for B, here we have a returnless system, so there is no return line here. And then C, we have a demand control system with no return line. And you can also see individual component there. Number one, we have the fuel tank, and then number two here is showing the electric fuel pump. this one. And then number 3, I think this one is filter. See, here is fuel filter. Number 4 is high pressure line, and so on. And then with a direct injection, usually the liquid fuel, which is normally gasoline, must be injected at high pressures, since widespread dispersion and then deep spray penetration and small droplet size are required. Why we need to have this one? Because the preparation time is much shorter than the intake manifold injection. This feature is showing an example of the fuel supply system for DI operating condition. Last topic is liquid petroleum gas and natural gas. Liquid petroleum gas, LPG, so this is a mixture of propane and butane. Okay, so this is the main component of the LPG, propane and butane. So this LPG can be stored in a cylindrical tank, so in the liquid state under pressure up to 27 bar. Okay, and then the fuel volume is regulated to 80%, so it means we still have 20% void volume there to allow liquid gas to expand at higher temperature. So this LPG, when used in engine, so it is injected into the intake manifold, okay, in similar fashion to multi-point gasoline injection. And it may be vaporized in a pressure regulator prior to injector, or may be injected as a liquid and then vaporized in the intake manifold. So once again, it's pretty much similar to the multi-point injection in gasoline fuel. So the fuel system uses an exhaust gas oxygen sensor to maintain a closed loop stoichiometric mixture control, so especially when we use a three-way catalyst to remove CO, NOx, and unburned hydrocarbon. And then because its fuel molecules, in this case propane and butanes, are smaller than those typical of gasoline, so you know that the molecular weight of this propane and butane is much smaller than the gasoline. So gasoline can be represented by this one, C7H13. So the LPG fuel vapor displaces more air in the fuel-air mixture, and accordingly the engine maximum power and torque are reduced by about 5%. Okay, and then due to its higher HC ratio, so use LPG produces about 10% less CO2 emission than equivalent use of gasoline. This is a good thing of having LPG. So once again, it has a higher HC ratio, which result in less CO2 emission. And then hydrocarbon emission with LPG are lower than equivalent gasoline engine HC emission. Next one, natural gas fuel. So natural gas is one of an attractive alternative fuel, and currently we have several ongoing projects looking at engine design and analysis using natural gas. Natural gas is used as a spark ignition engine fuel for both in vehicles as an alternative to gasoline, and in buses and larger engines for power generation as an alternative to diesel. So natural gas fuel price is lower than gasoline and diesel. So natural gas is mainly composed of methane, CH4, so whose concentration can vary from 80 to 100%. It is usually stored on the vehicle as a compressed gas in a high pressure, can be up to 700 bar, in cylindrical reinforced tank. As a compressed gas, its stored energy density is about 4 times lower than that of liquid hydrocarbon. So liquid hydrocarbon here is gasoline and diesel fuel. Natural gas engine fuel system operates similarly to those used in multi-point injected gasoline engine. So natural gas is usually injected in the intake manifold. And then due to its displacement of air in the fuel-air mixture, natural gas power engines have about 10 to 15% lower output than when operated with gasoline. So natural gas, which is mainly consists of a CH4, and CH4 has much lower molecular weight than gasoline and diesel. Therefore, it will displace more air, and in this case, it is about 10 to 15% more air displaced by natural gas. However, natural gas has a high anti-knock octane rating, which as a standalone fuel would allow significantly higher engine conversion ratio. So natural gas octane number can be up to 120. So gasoline has octane number 90, 92, 95. Okay. So because of this higher octane number, we can design an engine with natural gas with higher compression ratio. So right now we can design natural gas compression ratio up to 13 to 1. Gasoline engine compression ratio, so it is 9, 10, maybe 10.5. And then variation in natural gas composition. So in practice, reduce this knock benefit. So if we can have, let's say, close to 100 methane inside natural gas, then it's good because methane has the highest anti-knock compared to the other natural gas components. So if the natural gas contain more propane and butane, then we will have a lower octane number. And then natural gas engines have a lower CO2 emission by about 20 to 30% due to its lower CH ratio than gasoline. Okay, so natural gas, if it is, let's say, 100% methane, then we have CH4, so it has much lower CH ratio or much higher HC ratio compared to gasoline. So gasoline, we can represent it as, let's say, C8H18. So in this case, we will have much lower CH ratio than the one for gasoline, which finally result in lower CO2 emission. Last one here, methane as a major component of the hydrocarbon emission is not photochemically active in the atmospheric smoke chemistry, although it is one of the significant greenhouse gases. So one of the research topic on this natural gas engine is on how to reduce methane slips, which means to reduce methane in the exhaust gas. Okay, we have completed this mixture preparation in spark ignition engine. You have a great day.